Okay, so the first lab I'm going to show you, this is Chem 121, is that we're going to be doing the gas laws, and we're going to look at Boyles Law, Gay-Lussac's Law, and Charles' Law. There'll be 3 separate videos to do this. The first one will be Boyles Law, Charles' Law, and Gay-Lussac's will come after this one. For the first 2, Boyles Law and Gay-Lussac's, we'll be using a probe, which is just it's a way of measuring things results digitally. And the name of the company is Vernier. They've been making probes for a long time. You may have used these. I know, middle school teachers that have used these types of things before. So they're quick, simple types of instruments used to get us really pretty good data. So so what we have is we have an interface, this guy here, and then what we're going to be using is a pressure sensor. And the way that we're going to vary the pressure and the volume, that's the one thing about these, is that they have wires. Actually, we have wireless. I'm not going to use that. I'll use that when we finally come back to class, whenever that'll be. So we're going to be using a syringe to measure, change our volume and measure our pressure. So the syringe goes from 5 mils up to 20 mils at 1 mil increments. So technically we'll only have, we're measuring to the ones, okay? So, and remember every digit, so we measure to the ones, we're allowed 1 more digit, so we can write down, technically, 1 more digit than we measure, so maybe like 5.5 or whatever. Okay, and so we got to be careful about that. So, so first thing I'm going to do is set the syringe up, and in the instructions, if you look, it says set it up for 5 mils. And so I put 5 mils of, so there's 5 mils of air inside our syringe now. And I'm going to hook this up to the sensor, okay, and like so. And then what we're going to do is change the volume by pressing or by pulling out the syringe, and then measuring what happens. So the pressure that the pressure gauge measures. Okay, so the next thing I'm going to do is I got to set up the program that's going to measure the data, and that's what we have here on our screen. So let's get a closer view of that. Okay. All right, you'll notice is that it says Boyles Law, and I'm going to double click on that and get what I need. Okay, so here's the program's already set up to measure Boyles Law. And you'll notice in the left, in the Y column, is, let me get it better. Okay, Y column is pressure in kPa. We can measure atmospheres or kPas or torrs or whatever. It doesn't matter at this point. What we're going to do is get a relationship between volume and pressure, and the pressure that we use is it just depends on what we're going to do. The program uses kPa. If you go back and look at notes, 101.1 kPa is equal to 1 atmosphere. Now you don't have to know that. Just let you know what kind of things to expect as we go. Now in the okay, on the x-axis is the volume. All right, so, and over here is a column that we're going to put the data in, and then it's going to be plotted on our graph. So the first thing I'm going to do is I'm going to take measure the pressure of the 5 mils and record it, and then change the appropriate pressures by moving the plunger in and out. Now, okay, so there's a button up here that says collect, and when I hit that, that'll let me to start to start collecting and recording the data. So I'm going to do that. Okay, so now what I can do is, if you look down here, it tells me a value. The value says 88.41 kPa. That is the volume inside the syringe. I mean the pressure inside the syringe now. And so I want to record that first. Okay. So the way to do that is hit keep. And what I do is it'll ask me the volume that's inside this syringe. Now, it says 5.0 mils, but we have to put in 0.8 because that's how much is inside the tube. So we have to include that as well. So we're going to put in 5.8 mils. It's already, the units are already taken care of. And what it does is it plots that first point into appropriate place. Okay, next thing I'm going to do is I'm going to move the syringe. Okay, I'm going to move the syringe out. Well, I got to redo it because it was at the wrong volume. That's fine. So let's stop and redo. All right, so actually I'm going to start over. Okay. Whoops, where'd it go? There it is. Killed it. All right, so here it is. Okay. So the syringe says 5. I want to collect that first point. Okay, that makes more sense. 100.62. It should be barometric pressure inside the volume in the syringe. So it should be around 101. So that makes more sense. I'm going to collect that data. So I hit collect. Ask me if I want to keep it. I say yes. I put in 5.8. Okay. All right, next thing I'm going to do is I'm going to change the volume in the syringe. Okay. So I'm going to change the volume to 7. Now it requires a little bit. I'm going to have to hold it there. If I let go, it's going to go back down to 5. So I'm going to have to hold it there. And I'm going to have to record the data. Okay. And again, it says 7, but really I want to put 7.8. Okay, I got 2 points. All right, so now I'm going to go out to 10 mils. So it's even harder to pull. Okay. All right, that's how much pressure I have to apply, but you're actually reducing the pressure inside inside the syringe. Okay, so now I'm going to record that, and I'll put 10.8. Okay, now if you look at the curve, you see it looks like it's what you kind of expect. As you decrease the volume, the pressure is going down. So now I'm going to go to 15, as close as I can get. Okay, keep that point, and call 15.8. And then one more, I'm going to go all the way to 20. Okay, and keep that one recorded. And now it's 20.8. Okay, now I want to go the other way too. So I'm going to actually decrease the volume as well. So I'm going all the way down to 5. And so let's go to, I'm going to go to 3. No, let's go to 2 and record that value. So I'm going to go down to 2. Okay, and I'm going to keep that one. Okay, it says 157, so that can make sense, is that I'm applying more pressure. And this is 2.8. And there you go. So there's my data. So we're done. That's how simple this experiment is. First, in terms of doing it, but actually it's got a lot of information. So I'm going to stop it. And now what I'm going to do is we're going to analyze the data. So let's see what it looks like here. Okay, so if you take a look at it, you can see that there is a definite relationship between, right, we have value up here all the way down here. Now, let's see. So what we want to do now is in your lab book is what we want to do is actually find out the mathematical relationship between the volume and the pressure. And so what we're going to do is there's a feature on this is that you can find a fit, okay, and so let me get rid of that. So what we got here is there's pushing on, there's up here in the toolbar, there's f of x equals something, and there's different equations that could fit your data. And what we're going to do is we're going to go through several of them and trying to find the best fit. And the first one is the relationship, is a linear relationship. So it's y equals ax. So that's simply proportional. And what I'm going to do is I'm going to hit try fit and see what it comes up with. All right, and if you look at it, it came up with a kind of a weird line. It's in this line, when we use the first ax, it goes in the opposite direction. Okay, so I don't like that one. So I'm going to go to the next one, mx plus b, see what it gives. Okay, now this is better. All right, you can see that it goes in the same direction, but it's not hitting the points that it does a pretty good job. But let's see if we can find another graph that may be better for what we want to do. Sorry about that. Okay, so what I'm going to do now is, now there's a series of polynomial equations that we can use, and let me just go over a couple of them and see what you can see out of them. So the first one is a quadratic, and let's see what it fits. Okay, now you can see that the quadratic, which is the formula is of the form ax squared plus bx plus c. It actually looks better than the linear. Okay, so let's keep that one as a good one, as a possibility. It seems to be better than linear, but let's check out other ones. Okay, now I'm going to go use a cubic polynomial. And if you notice, that one looks really good, okay? It hits all the points. So is that our best line? So this is of the form ax, ax, a plus bx plus cx squared plus dx squared, okay? And we have numbers that deal with it. But it seems like you may want to just stop and go use that one. But I don't know. Let's think about that. Now, if you know what a cubic line looks like, this does a good job of predicting what this very small range of cubic. But if you know a cubic line, what it does, a cubic goes down, and then it goes up, and then it comes back down. Okay, so it would, if this was a cubic, and we extrapolated, we would see it go up and then down, right? And I would hope that a relationship between, as we increase or decrease the volume, that as we increase the volume, the pressure keeps on going down, that it doesn't increase at some point. All right, we don't, I mean, it's possible that I could do something weird like that, but if you think about it, the cube is a nice fit, but it doesn't make sense. In fact, all of the rest of the polynomials won't really make sense. They might have really good fits. For instance, if we go to the next one, it even fits better. And then the fifth even works better. Okay, but what we're seeing is a very small range of that, what that curve actually looks like. For a fifth, it goes up, and it has 4 bumps in it. Okay, so a polynomial really is not a good fit for it. So what's better? Right, so let's try it's ax to the b power and see what we get that. Okay, ax to the b actually looks like a pretty good fit. Okay, it's better, and it doesn't. And if we looked at it, would run out indefinitely. Now we can use this one, but a better fit is to realize what's going on here, what's happening with this graph. Okay, and we get this from Boyles Law. And Boyles Law says is that the pressure is inversely proportional to the volume. So is there an equation that gives an inverse relationship? And yes, there is. It's a over the x, and that one is really our best one. Even though it doesn't seem to fit the best, it's supposed to be our best one. Okay. All right. Now I don't know why it's not fitting as well as it should, but it's the one that we should use. Okay. And so what we will do is we'll record these values. So the equation y over y equals a over x, and the a is 496.9, and the RMSE just gives us the root mean squared, which is how much deviation it's off, is 18.86. And you would write all this information down if we were interested in it. But so in the equation it asks us which curve is the best. Technically, of the graphs so far, okay, there's several that are good. Like there's one here, a equals the log of b, the x, that one fits really well. But technically it should be a over x. All right, so we're gonna just use a over x. All right, so okay. So we would write this, it's pressure equals, so y is where pressure is, so this would P equals A over, which is 496.9 over V. All right, so that's Boyles Law experiment. Okay, I'm going to set up Gay-Lussac's experiment next, and we'll go over that one as well.